Hello everyone, thank you for joining me. My name is Zahir Patni and I'm a Senior Advisor for Research Science at Peraton Labs. Today we're going to be talking about SEDIMENT and specifically how remote attestation can be incorporated in an environmental sensor use case. First, we'll start out with an overview of what SEDIMENT is. Then we'll talk a little bit about the use case itself and the different components involved. Finally, we'll take a look at a video of the SEDIMENT in action. So what is SEDIMENT? SEDIMENT stands for Secure Distributed IoT Management. It uses a combination of software root of trust, remote attestation, as well as resource-efficient cryptography. And it builds a system that scales across heterogeneous computing platforms. The aim here is to provide a secure remote attestation framework that can be leveraged for lightweight, resource-constrained devices. We've been working closely with the Linux Foundation, specifically with the 5G Super Blueprint. We already have one entry in the library there, and we're currently working on a second. There's a link here to the 5G Super Blueprint white paper that includes a little information about SEDIMENT as well. So moving on to the use case. For this use case, we're going to be demonstrating SEDIMENT and how it can be used to authenticate lightweight, resource-constrained IoT devices, specifically for this case, environmental sensors. SEDIMENT, which uses the techniques and methods outlined above, is used to control network access for these lightweight, resource-constrained environmental sensors. This is the layout that we have for the demonstration. For this demonstration, we're using Raspberry Pi Zero W devices. We have 4 of them, and each one is paired up with the Pi Moroni Enviro sensor. We can see on the left-hand side that the Raspberry Pi Zero is connected to the network via Wi-Fi. On the right-hand side, we see all the SEDIMENT servers. These are connected via Ethernet. Starting from the top, we have the remote attestation verifier, followed by the revocation server, then the remote attestation manager, the message broker, and on the far right, we have the application servers and subscribers. We see there's a few different flows here. First, we have the SEDIMENT protocol, which is shown here in blue. We see it on the left with the Raspberry Pi Zero, and flowing over to the SEDIMENT servers on the right, with the remote attestation verifier, the manager, as well as the application servers and the revocation server. Once each device has successfully completed remote attestation, they're then allowed to go ahead and publish data throughout the system. We see this flow in red, and basically the way this works is the Raspberry Pi Zero gains the sensor data from the Enviro sensor and then publishes messages out over the SEDIMENT network. It flows through the remote attestation manager, through the message broker, and then finally to the application servers, which are subscribing to this data. So now let's talk a little bit more about each of these components. First, we have the remote attestation verifier. The verifier runs on a remote attestation protocol known as a RAP server, and it basically makes attestation decisions about the well-being of each of these targeted IoT devices. And it does this by evaluating the supplied evidence against the verifier's internal knowledge of the properties of each of these targets. Next, we have the remote attestation manager. The remote attestation manager serves in an administrative capacity and pairs up each of these IoT devices running a prover with the verifier that they'll be communicating with. The remote attestation prover runs on the targeted IoT end devices that we're interested in and supplies the evidence concerning the properties of each of these targets. The evidence is gathered by means of network endpoint assessment, which collects and safekeeps and produces the evidence in response to attestation challenges by the verifier. And then finally, we have the message broker. The message broker utilized for SEDIMENT is Eclipse Mosquito, which is just an open source message broker that implements the MQTT protocol. Any other implementation of MQTT can be substituted here. On the right-hand column, we see links to each of these components. For the remote attestation framework, we've open sourced it with the Linux Foundation, and you can see a link to our repository there. There's also a link to the Mosquito broker as well. So this is just an image of the 4 IoT devices. It's just the 4 Raspberry Pi Zero W devices, each one paired up with the Pi Moroni Enviro sensor. There's quite a few different sensors on there. There's light, proximity, humidity, as well as a few other sensors. And you can see there's also a built-in screen on each of these sensors. Currently, it just shows the name of the device as well as the IP address. So now we'll take a look at the video of this use case demonstration. First, we're just going to start off by starting each of the sediment servers. And then we'll go ahead and start the sediment GUI. Here we can see the GUI is loaded for remote attestation before any of the devices have actually performed remote attestation. Next, we're going to go ahead and start the provers on each of the IoT devices. And so here again, we're looking at the remote attestation GUI. There's a few different columns here. Starting from the left, we have the device ID. Then we have the time that the remote attestation was performed, the elapsed time for how long the remote attestation took, the remote attestation status, and this is either correct or incorrect. And then finally, we have the server that's reporting this remote attestation result. So for this use case, we're using one wrap server. So each of these IoT devices are attesting to the same server. So here we can see all the IoT devices have a correct status because none of them have been modified since they were initially deployed. Now we'll take a look at the application server GUI. And this is basically going to graph each of the sensor data that's being received from each of these IoT devices. We have a few different sensors shown here. Starting from the top left, we have the temperature. Then moving to the right, we have light, then humidity, proximity, and then at the bottom, if you scroll down, we have pressure. So here we can see data coming in from each of the IoT devices. The first IoT device is shown in red, the second in green, the third in blue, and now we're starting to see the fourth one in pink. So since each of these IoT devices has successfully completed remote attestation, SEDIMENT is allowing the data that these devices are publishing to be shown throughout the system. So here we can see two of the data streams have actually stopped, notably the blue and the green. And we can see that the other data streams for the red and pink devices are still continuing on. Next, we'll take a look at the remote attestation GUI again to see why these two devices have stopped reporting data. So we can see here that of the 4 devices, the 2 in the middle are now showing an incorrect status for remote attestation status. And that's because these devices have had their firmware compromised and have failed subsequent remote attestations that have happened. So since these devices have failed remote attestation, SEDIMENT is actually blocking the data from these devices from entering into the system. Since we no longer trust these devices, we don't want to act or process the data from these devices. We can see that there's no interruption for the data between the other 2 devices shown in red and pink. So the data for these 2 devices that have failed remote attestation will continue to be blocked until they successfully pass remote attestation. And this can be done by, an operator going to these devices, reflashing them, and basically returning them to factory operation. So next, we're actually going to physically move one of these devices, namely the device shown in red. And we're going to basically move it from a shaded area to the windowsill where it's in contact with the sunlight. We can see the temperature reading is slightly starting to increase here because of sunshine. We see a great increase in the light reading, as well as a quick blip in the proximity as well as humidity. And the blip in proximity and humidity is due to the hand being close to the sensors and it detecting the change there. We can see that the temperature is slowly beginning to rise because it's in the sunlight. and we see the increased sensor readings from the light. So next we're going to go ahead and move this device back from the sunshine back into the shade, and we'll see changes in the temperature reading as well as the light reading. So here we can see that the light reading is basically returned back down to the baseline. We see some changes in humidity as well as proximity as well. And if we take a look at the top left of the screen, we can start to see the temperature reading is coming down slightly. So now we're going to go ahead and stop SEDIMENT running on each of these IoT devices, and we'll see the data flow stop from each of the devices. So we can see here that the device shown in red has already stopped, and the pink one has not been stopped just yet. And we see now that the pink one has stopped as well. So there's a few other things I'd like to show. So in the presentation, there was links to each of the open source components that we have for the remote attestation framework. And if you take a look at the base of the repository for remote attestation, we have a bit of a README here that kind of goes over a high-level overview of what SEDIMENT is and the different components of it, as well as basically how to set it up, build it, and configure it. It talks about the different third-party libraries we use, namely MQTT, as well as Embed TLS. It talks about the build process, and basically shows you how to run this all on a single Ubuntu machine for testing, and the configuration device, the configuration parameters for each of these different services, as well as how to run them with the different parameters that they provide. It goes over a simple test configuration that I described, running all these components on an Ubuntu machine, as well as how to run it on a Raspberry Pi Zero like we did for this demonstration. It goes through the build process on the Raspberry Pi Zero, as well as how to configure it in the system. And then it also talks about using Zephyr. So we've also experimented with some devices using Zephyr, namely Silicon Labs Giant Gecko. And the build process is a little bit different. So if you follow this link here, it'll bring you to this README. And this will go over basically the instructions on how to set up and flash a Zephyr device. So the initial steps are to install the Zephyr SDK. And then it talks about how to build SEDIMENT on the Zephyr device, as well as how to flash the Zephyr image over to the device and configure it for the system. Finally, it talks about how to connect to it over serial, as well as how to test it. And then I also just wanted to quickly show the 5G Super Blueprint white paper that I was talking about earlier. So this discusses quite a few different use cases we have within the different components within the 5G Super Blueprint. And SEDIMENT is actually covered in 3.6. It's on page 15. So this actually talks about our cooperation with AccuNox, specifically with CubeArmor, and discusses the use case that we have there and how SEDIMENT can be used there. And it talks about not only remote attestation, but also scalable cryptography and root of trust. And as I mentioned, we're working on a second use case with the Linux Foundation, which will be incorporating this demonstration and the sensor use case into the Super Blueprint as well. So with that, any questions? In the front?
You didn't explain how does it verify that it's authentic?
How it successfully completed remote attestation?
Not the procedure, but what kind of parameter that's used to make sure that it's proven or verified
So like what components it actually checks to see if it's verified?
if it's changed, the original.
Right. So there's a few different components that we actually check for remote attestation. One of them is boot time. One of them is the OS name and version. Then for smaller IoT devices like the Giant Gecko, which have pretty limited flash storage, we do a full fingerprint of the entire OS image firmware. And then we also have user-defined functions that we implemented to allow SEDIMENT to run on Linux as well. So with Linux, we can have much larger devices with much larger storage capacity, and we don't necessarily want to fingerprint the entire storage system. So basically with user-defined functions, it allows for configuration to provide which parts of the Linux operating system we want to actually verify. So for example, we can verify the SEDIMENT binary to make sure it hasn't been compromised. We can also attest configuration files to make sure they haven't been changed since deployment. And we can also incorporate third-party tools that check and run against different parts of the system and ensure that those tools have not been modified themselves so that we can actually trust the results provided by those tools.
I understand, but how do you know, for example, like you're dependent, the part running on the IoT connecting to your system is reporting real information, but that itself can also be hacked. Is there like a shared secret making sure that this part is original and
Yes.
right?
Yeah, so like,
Between and just do like a retransmission.
so like a replay attack.
Yeah.
Yeah, so there's nonces and stuff that are used to ensure that each response is unique to the request that was being sent to it. So, if a device is not compromised, it has a successful remote attestation response, it can't be replayed later after it's been compromised because there's some changes to the request that require corresponding changes to the response. Did that answer your question? Okay. And there was another question in the back?
Yeah, following that, so you're not using, on the Raspberry Pi, you're not using an EVM chip?
Correct, we're not. We're basically using a generic Linux solution for that currently. We're investigating some, specific hardware does have root of trust, and we do leverage that in some use cases, but for the Raspberry Pi, we're using a generic Linux implementation.
Yeah, because you can get a dollar card for the Raspberry Pi.
Yeah, we were looking at kind of just using the Raspberry Pi out of the box without any add-ons just yet.
Okay. The other question I had was, so the attestation protocol, are you elaborating this on the standard way of formatting evidence? And the IETF remote attestation working group has been working on stuff.
Yes.
How you format evidence.
With rats?
Yeah.
Yes.
Okay.
Yes.
Great.
Any additional questions? All right, with that, thank you very much for your time. I appreciate it.